So over the next few days, our big goal is to find out or to be able to predict what the shape is of actual molecules. And if you can predict the shape of a molecule, then that gives you a real handle, a real clue on what its boiling point might be. Just a lot of its properties. It's what it will and will not react with. And this gives you a lot of insights into what a chemical can and cannot do if you know its shape or why it does what it does. So that's kind of our big goal. And bonding made simple is how we're going to try to do this. The electron dot symbols or electron dot formulas or Lewis formulas or Lewis structures. All that means the exact same thing. And here's some of them right here, what they're going to look like, for atoms anyway. Okay, and that's our starting point. Let's see if we can remember a few things first, though. Jasmine, please give me a chemical formula of a salt. Any salt. Now, I'll give you a hint. Salts you had to name the cation first, and then you name the anion. Okay, what would be an example of a salt? Any cation, then any anion. Somebody help her out? NaCl. Okay. Not NaCl, though. That's too easy, because salt is, you think of NaCl. But that works. That works, though, because you said sodium, that's Na+, chloride, that's Cl-, so NaCl. So not NaCl, though. Priscilla would be another one. That's too easy. Okay, you use K. K as a plus. K, and what anion do you want to put on there? Cl, you can do that, all right? Potassium chloride. There's a bunch of them. You could pick iron 3 and sulfate. Remember playing this game? So you have to put the 2 down there and the 3 there. There's a whole bunch. There's a gazillion of these salts. Just have to name a cation and an anion. Now, all of these salts, April, are held together by ionic bonds. So what is an ionic bond? What's about an ionic bond that holds this stuff together? What's an ionic bond? What's the attractive force that's holding stuff together? The what? The negative and positive, right? Opposites attract. So that's exactly what's holding all this stuff together. Pretty strong, too. Okay, let's take, these guys have really high melting points. Okay, a molecule. Eric, how about a chemical formula of a molecule? And you can't say H2O. I'll give him this isn't much of a hint, but I'll give him a guide. You can't name a what? It's just an M. Whatever he tells me, you can't give me one of these. Metal. Don't give me a metal. Has to be really. CO2. 2 nonmetals is what he has to do. Now, we're not supposed to say CO2 either, Alyssa. There's not much job security there. How are you supposed to name that? Carbon dioxide. You have to count to 10 in Greek. Monocarbon dioxide. Okay. Now, covalent bonds, that's what holds molecules together, Jesus. What is a covalent bond? What's the attractive force going on there? It certainly isn't pluses and minuses holding things together. What is it? I think it's really abstract. It's not gravity. I can't relate shells as you're getting there. Remember you had these orbital ideas? And I don't know, you pick, let's just pick an easy one. Oxygen, right? So you have this OO bond. So all I'm saying is you draw the little orbitals on this oxygen, whatever shape they are, right? You draw the little orbitals on the other guy, whatever shape they are. But the point is there's some overlap. These electrons, they overlap. What does that mean? That means the electrons, do they belong to this oxygen? Or do they belong to that one? Nobody knows. They're just being shared. And that's a very strong cohesive force. It takes a lot of energy to break it. So that's all it is technically orbital overlap. Or just sharing of electrons. Okay. Nobody knows whose electrons are whose. They're just between they spend a lot of time between those two nuclei, those two oxygen nuclei. Okay, that's our little review. Lewis electron dot symbols. They're going to call them Lewis electron dot symbols. They're going to call them, what else would they call them? Electron structures, maybe? We'll see some other questions for them. But we're supposed to draw Lewis symbols for atoms and ions. Now here's for atoms and ions. Now here's a bunch for atoms, Caroline. How would you describe the rules for doing this? Okay, the number of electrons are going to be the dots, right? And then you put that around the symbol. She's really, really close. Kelly, the problem with what she said is, can you see this one, Kelly? How many dots are around that O? 6. Now, if you look up at oxygen, oxygen has how many electrons total, though? Has 8. Why only 6 dots? Well, it's the group number, but exactly. But it's the what type of electrons? The outer ones, but we're supposed to not say outer electrons. We're supposed to say valence. It's the valence electrons. That gives you the number of dots every single time. Look at that. All these guys that have 1 valence electron, 2 valence electrons, and on, right? Okay. So that's how you write them. How would you write the Lewis symbol then for Paul? Carbon. How would you write the Lewis symbol for carbon then? I'll get you started. Put the C. It's not much help, but then use a periodic table to figure out how many dots there are. Carbon has, 6 total, but the group number is a 4. It's a Roman numeral, a 4. Now you just spread out the 4 dots as much as you can on the 4 sides. That's how they like to do it. And if you do that, it'll help you what's coming up tomorrow, next class period. How about C plus 1, Monica Soto Ruiz? I'll help you out. I'll put the C. How many dots? That's the question. Is there going to be 5 or is there going to be 3? It's 3 because you don't have enough. It's positive charge. They ripped 1 off. So you put 3. Separate it out. And you're going to get points taken off if you leave it like that. What they want you to do every single time is put brackets. Now you can put in a plus 1 as a charge. You can put brackets all the time. It doesn't hurt anything. But don't put a charge if there's no charge. Right? So you can always put brackets, but you have to put brackets when it's an ion. Jasmine, C negative 4. There's the C. So how many dots? Would it be 8 dots? You're starting out with 4, negative 4, so that means you have 4 extra. 8 dots, yep. So you figure out how many valence you have in the first place, right? Oh, and I have 4 extra, fine. Not done. Got to do the brackets. Okay. Now let's see if we can make the leap here, Priscilla. C negative 4. Does that sound familiar? We had a name for it. That was the ion that carbon formed. What did we call it? Carbide. We hardly ever saw it, but it is carbide. Okay. How did we get it? April, how did we figure out that carbon has a -4 charge? We used the periodic table. How did we get it? Here's carbon. We counted over to the what? To the nobles, right? 1, 2, 3, 4. Carbon had -4. How about nitrogen? Nitrogen has a -3. 1, 2, 3. How many dots would you put around a noble gas? If I said draw its Lewis dot structure. How many dots would you put around it? 8. Every single noble gas has 8 valence electrons. Well, Eric, what's supposed to be the most stable situation up here for electron configurations? What is everything after? They want all these elements really want the electron configuration of what? Same as what? And they're going to be noble gases. Noble gases. So really, forget about all the inner electrons. Just look at the outer ones, the valence. Everything really wants 8 valence electrons. So that's why this carbide is so nice and stable, because it has 8 valence electrons. Same as a noble gas. Oxide, right? It has 6 to start out with. We give it 2 more, and it would have 8. Right? Bromide, it has 7 to start out with. Give it 1 more. Noble. So that's why we did. That's why this counting over to nobles worked, to get these charges for these ions, because then they'll have the same valence as a noble gas. A few questions here. Why does aluminum form Al+3? Alyssa. Why would aluminum is right here. Why would it form the ion +3? Now the hint is to kind of imagine what the electron configurations are. Aluminum +3. If aluminum lost 3 electrons, it would have the same electron configuration as neon. That's why aluminum was only +3. Remember, we had to memorize it? Aluminum's only +3 because it loses, right? 1, 2, 3. 1, 2, 3. I have neon. So that's why. How about, this is kind of a trick question, but might as well talk about it. Gallium, indium, and tellurium, well, they're right under aluminum, but they form +1. They might form +3 too, but they definitely form a +1. Do you see the difference? Aluminum doesn't have this full D shell right below it, but these 3 do. So they lose 1, boom, now they're at the D10 and they can quit. Aluminum can't do it. Aluminum has to go all the way to neon. So gallium, indium, and tellurium can stop at that pseudo-noble gas core. How about these? Why would you guess, Jesus, just playing around some more with this idea of electron configurations? Jesus, where's tin and lead? Where are they? Here they are. Why would you guess these guys form +2? Yeah, the same as the gallium, indium, and tellurium. You lose 2 and you've got your pseudo-noble gas core. Yeah. How about what ion would you predict for nitrogen? Caroline, what ion does nitrogen form? It's right here. And with a +3 or -3? And with a -3, because you have to give it 3 electrons, right? How about oxygen, everybody? O with a -2. F, -1, right? Okay. How about phosphorus? Kelly, how about phosphorus? What ion would phosphorus form? P with a negative 3. All we're doing is we're giving it the same valence as a noble gas. S, everybody, a negative 2. Cl. Yeah, I think you got the idea. Okay, another general question. Monica Soto Ruiz, if you had to guess what the charge is for some transition metal, a common answer, or the most common charge in here for these guys is +2. I mean, it ranges all over the place, but the most common one is +2. Why would that be? Does anyone see why? All these transition metals have these guys in common. 4s2, 5s2, 6s2. They can lose those and leave this D stuff alone. That's why. So it's just an observation that all those transition metals have 4s2, 5s2, or 6s2 that they can lose. Okay. So we're going to do this first one together, then we'll go to the boards and knock out the rest of them. Write the noble gas core notation for each ion. Iron +3. Let's pick on Jasmine. Iron +3, Jasmine. Noble gas core notation. So where would you start for iron +3? Where the heck is iron? Here's iron. Number 26. So how would you start writing the noble gas core notation for iron? AR in brackets, exactly. Okay, we'll put AR in brackets. Perfect. Priscilla, then what do we do? Okay, now we want to AR, now we're down here. So this would be 4s2. Okay, we're not there yet. Okay. April. Okay, here's the question, April. Do we want to stop 1, 2, 3, or do we want to stop 1, 2, 3? You have to go back because we're losing electrons. So we want to stop here. She's right. So, Eric, stop here. That means what? 3d3. 3d3. Okay. Alyssa, can we go to the boards now, or? It's a trick question. Yeah. Oh, because positives to make cations, you have to lose electrons. To make anions, they're extra. You have to add them on. So iron +3, you have 26 electrons. To make it iron +3, he only has 23 electrons. He's still iron, but only has 23 electrons because you subtract 3. He's 3 short of being neutral. So it's going to be the same as vanadium. So take away electrons, cations. Okay, back to this guy. Iron +3 is really... Iron doesn't form all these different cations. It forms iron +3. Why? You remember this? When you write these electron configurations, you're supposed to check for 2 things before you can move on. Can I form D what or D what? D5 or D10. This is one of those cases. There you go. This is why iron +3 forms. Is because of whose rule? Starts with an H. Hund's. You're going to have these 5 d orbitals, each with an electron all pointing up. Very, very stable. Or all pointing down. Doesn't matter. 3d5. Okay, so let's go to the boards and we can knock out the rest of these and call it a day. So we want to write the noble gas core notation for indium +1. Write the noble gas core notation for indium +1. Now, if you don't have chalk, does anyone not have chalk? Everyone has chalk? You guys don't have chalk. I'm going to have to go get some. Or break off Eric's. I've got a bunch in the other room. So go ahead and start. I'll get some more. You get brand new pieces, yeah. You have to write with your fingernails. Oh, maybe you do. Oh, it's all broken in there. Sorry. Okay, did you get an answer? Indium plus 1. Where is indium? Okay, so you ended up with 4D10. Stop there. Looks good. If you stopped with 4D10, let's do the next one. What? Wrong one. Oh, sorry, yeah. That's right. 5S2, 4D10. And the krypton. Yeah, you have to have the krypton in there too. So write Lewis symbols for the following. Now, they're going to call these Lewis symbols. They're going to call them Lewis dot structures. There's all means the same thing. Write Lewis symbols for the following. P minus 3. These guys are just in pieces. P minus 3. Then do the same for Ga plus 1. Now remember to get these, figure these out, find phosphorus, figure out how many valence he has, and then it's negative 3. So he's got 3 extra electrons. And don't forget, you need the brackets and the charge. Can you put these on that tray behind you? Thank you, sir. And gallium just loses 1. So you should just have 2 dots around him. Oh, I think for the gallium, where do you leave the dots? I think it's probably best like Priscilla has it. You spread them out as much as you can. But it really doesn't matter. There's no right or wrong answer there. I just wouldn't pair them up. Okay. Use Lewis symbols to represent the transfer of electrons between the following neutral atoms to form atomic ions with noble gas. Now, I think what we should probably do on this next one is cheat a little bit. Because if you took calcium and bromine and you put them together, what would you end up with? Calcium always forms, because all of what we did before all still works. Calcium always forms what ion? Calcium plus 2. And what did bromine always form? A minus 1. Okay? So if you're going to write the formula for this thing, what would it be? CaBr2. Okay. So when we write this reaction, we really need a Ca, a Br, and a Br. Okay? Now so on this side, write the Lewis dots. Lewis dot structures. Okay. On this side, you write the Lewis dot structures again, but with their ions. And what you're going to see happening is Ca has how many dots around them? 2. Bromine has how many? 7. So if he loses his 2, he's going to be the same as argon. So he wants to lose 2, that's why he's plus 2. Bromine, he has 7. He wants to gain 1 more, so he'll be the same as Kr, right? Then he'll be a noble gas too. So this guy is going to grab one of these electrons. This guy is going to grab one of these electrons. So you're going to end up with calcium over here with nothing. Well, you got to have the charge on there. And then you're going to have the 2 bromines with 8. So see if you can explain how calcium bromide forms. So go ahead and draw the reactants with neutral Lewis dot structures, and then you draw the ions on the other side showing how those ions formed. And really why it's CaBr2. So on the reactants, just write them out in their Lewis dot, in their neutral form. The Lewis dot structures for bromine, calcium, and then bromine again. And put calcium in the middle. So, so bromine has 7. And have a little plus, show it plus, that you were adding them up. They're reacting or something. Now, don't write ions on this side. Ions are going to end up over there. So no ions over here. Calcium needs how many dots? 2. Do you have 2 dots on there? Oh, okay. All right. And 7 and 7. Okay, now this bromine, he's going to rip off that dot. He's going to end up over here. This bromine is going to rip off the other dot. It's going to end up over there. And that's what you end up writing on that side. No, not yet. That's a product. There you go. It's on the product side. So this bromine, and for the product side, you end up having this bromine is going to rip off that electron. He's going to have all 8. This bromine is going to rip off that one and have all 8. Right? So on the product side, oh, Priscilla, you're close. Just don't forget your charges. You need brackets and charges. So on the reactant side, just have little pluses showing that they're adding up. All right? So on the product side, what you can illustrate over here is this bromine is going to rip off that electron. So that he's going to have all 8. And then this one's going to rip off that one, and he's going to have all 8. And calcium's going to be left with nothing. Well, no valence anyway. Yeah, good deal. Yep. And I think it's kind of helpful if you do something of like what Priscilla's doing here, because it kind of illustrates why we're doing this. She drew little arrows or something indicating where these dots are going. Right? So like this dot went over to this bromine. You got your R's. And this dot went over to the other bromine. Okay? Yeah, you have to have them. Yep. 2 valence. Yeah, you have to, because he's a Ca plus 2. Yep. If you don't, what's that?
That it could just be brackets showing that it has a charge?
Well, you can always put brackets, but if it has a charge, you have to have the brackets and the charge. So if it's neutral, you really don't need to write brackets at all. And the reason why the brackets are there is because that charge is distributed over the whole thing. That's really the reason for the brackets. Do the same thing for the potassium and iodine. Once you get it and it agrees with the folks around you, do the same for the potassium and the iodine. You can kind of cheat first and figure out what compound it's going to form. Put the number of valence on here, the number of valence on that guy. Yeah, perfect. Good deal. So he needs 7 though. 2, 4, 6. He needs 7. There you go. So then that he's gonna take that one. He's gonna have an extra one. He's gonna be short one. But they'll both have noble gas core notations. Okay. Okay. You're close, Monica. Just don't have charges on this side because they're neutral. You haven't transferred the electrons yet. Yeah. Yeah. The first part they're just neutral. Okay. For each of the following, write the noble gas core electron configuration and the Lewis symbol. So write the noble gas core electron configuration and the Lewis symbol for arsenic. Then for arsenic plus 3. So write the noble gas core electron configuration for arsenic, and then write its Lewis symbol. Oh, Priscilla, they don't like commas. Just straight. Yeah, there you go. Arsenic is way over here, so you got to go AR 4s2, right? Be 4s2, and then you keep going. Okay. Now, when you write this is arsenic, right? Mm-hmm. So you got to keep going. Though you're not at arsenic yet, because if you go to argon, you got to keep going. Argon, and then 4s2. Keep going all the way till you get here. So argon, 4s2, and keep going. 3d10. Arsenic, but arsenic, Monica, is right here. So you need 2p, 3p, 4p1, 4p2, 4p3. 4p3 yet. You're not at arsenic yet. Then you're there. And that's it. Yeah, because you have 5 dots on them. Yeah. You can see the 5 dots. It's going to be these 3 and those 2. Lewis symbols. P negative 3. Okay, so find P. P has how many valence? 5. And that's a negative 3, so you have 3 extra. So you have to have 8.
Oh, okay, so the dots. Okay.
You have 8 dots. And then you write negative 3 out there. So do them all. Keep going. Make sure your neighbors around you have the same thing as you. Good. Looks good. Mm-hmm. Yeah, looks good. Exactly. Well, so you got the idea. Good. 6. Looks good. Looks good. Eric, did you answer this one?
Yeah. P-3, right?
Why?
Because it's below N minus
Yeah,
3.
because negative 3s don't matter. They cancel
Yeah.
out. Yep.
And even if you do work on them, it's the same thing.
What's that?
I mean, you're still going to have lowering and lowering. You know what I mean? Like even if you do go over 3 spots, it's just like you said, they cancel out.
Yeah. Whoa.
Just because you're watching me,
What'd you do?
you gave her the oval.
The what? The oho? That looks good. Looks real good. So which one is this?
That one's arsenic.
Arsenic.
Plus 3.
Arsenic plus 3. Okay. Arsenic is supposed to have 5 dots. You subtracted 3, so there's just 2 left. Good. And they usually don't pair them up. They're going to spread them out. Looks real good.
And this is plus
Selenium.
2, so I just bracket.
And then right, plus 2. Yeah.
Do all of them have to be in brackets?
You can always do, even if it's original, you just don't write a charge. You can always do brackets.
Oh.
So either way, if you have ends above P, you know the ends could be small.
Get them all? Did you answer the last one? Why? Oh, larger radius, though, not. Remember, this is the smallest. Biggest is down here. P is bigger. P is bigger than N. Since they both have the same charge, you really don't worry about it. If you're done, there might be stuff in your folders. And the very last one, if you haven't, they're talking about N minus 3 or P minus 3, which one's bigger. Since they both have the same charge, you really don't look at the charge. You really just compare N and P. And P is bigger than N, right? So the largest would be P minus 3. Yeah.